Recording. Okay, so so originally we were going to do a midterm review, but I'm going to try to see if we can figure out a review time later in the week instead. So today we're going to start chapter 25. Before we get started, I'm just going to note another. I guess she's kind of like between different. I mean, she's technically a physicist because her name is Hilda Sin Araneda, and she was born today in 1933 in Chile. And her field is actually this thing called crystallography. Anyone ever heard of that before? What's crystallography? So some of you may have heard of it. Crystallography is a really cool thing, where let's say you have a bunch of let's say you just go outside and pick a rock, right? Pick up a rock, right? There's some structure to the atoms. So these are the atoms of that particular mineral, and through this thing called crystallography, where you just send in lights and figure out where they would refract, and through this thing called constructive and destructive interference that you guys learned about. Some of you guys, well, at least the ones who were here last semester, learned about waves. You can actually figure out the structure of those rocks, minerals, and whatever you want through this process called X-ray crystallography. This is how actually the DNA molecule was first discovered. What she worked on is actually more on the what's called the biophysics of protein crystallography, meaning all these little proteins inside us that does convert sugar into ATP to my muscle contracting, and my blood pumping, and fighting off diseases and stuff like that. All of this stuff, all this biology stuff that's happening inside us, all this chemistry that's happening inside us, is basically done by these little molecules called protein. And she actually studied how those proteins are, what the structure of those proteins are, how they're made, and it's actually one of the research field that I was actually really interested in after my PhD. If I didn't get hired here, this is probably what I will be doing right now. Basically taking little pictures of protein and see what they do and how they can actually enhance or be detrimental to life, stuff like that. So just to note, another type of physics is so if you were a physicist, this is one of the fields that you could work in if you want, and it's very linked to chemistry and biology. Okay. So now let's talk about electric potential, which is the next chapter. Electric potential is actually what we're more familiar with electricity in real life, because if you ever just go around, there's these little jacks around, right? That's 120 volts, right? That word volt is actually what's known as an electric potential. It's like the potential for it to have energy. Okay. So we're probably most exposed to it in our everyday life, but as good physicists as you guys are going to be, right, we have to figure out how we actually really define it from the perspective of how charges have forces acting on each other, how those forces creates electric field, which is what we've been learning before. So we're going to go all the way back, okay, back to, well, in this new textbook, chapter 9 and 10, on energy, okay? And we're going to try to figure out, how do we define electrical potential energy, how much energy is in these electrons and protons that we arrange in a certain fashion, okay? So just a reminder that if you have a force of some sort, right, let's say, I'm applying a force to this little chair, right? I'm pushing it, I'm applying a force to it. As it traversed over some distance, right, I am doing work on that chair, meaning I'm adding energy into the chair, right? So the complicated way to think about this is that, if you do the integral of force.dx, basically think about this as you're applying some force over some small distances, little tiny distances, but then you add them all up, right? And that's the total amount of work that you did on that system, okay? once again, since this is a dot product, it tells you how parallel the force and the displacements are to each other, right? So if I'm pushing this horizontally, right, I'm doing the maximum work. It's actually running away from me, but I'm pushing it. If I'm pushing it straight down, but I want it to go in the horizontal direction, now they're perpendicular to each other, right? Now I'm doing no work on it. I'm just kind of breaking the chair instead, right? So hopefully this dot product also makes sense. If you want to do work on something, right, you want to have it parallel to the direction you want it to move, right? You don't want it to be perpendicular, right? So we're going to go to an analogy first before we go to electricity, where let's say we have an object that's moving in a gravitational field, right? Meaning I take an object, right, and I just let it drop, right, from up here to the ground, okay? So the force of gravity is pushing it downward, right? We already know what that force is, force of gravity, right? It's the mass of that object times the acceleration of gravity. Usually it's just g in the negative j hat direction, right? It's pointing downward. Okay. As my little pen falls, right? Gravity is doing work because gravity and the direction that the object displays is the same, right? So the dot product between them is actually zero. The angle is 0 degrees. So you have the force of gravity times the distance that it moved, right? Cosine of 0 is 1. And since this is a constant force, once again, we can bring this out. And that allows us to just kind of get the use the magnitude of the force and skipping all the integration stuff, right? And the distance, delta r, that is displaced, right? It started at some initial y. I'm going to do a little dotted line here. And then let's say it ended at some final y position, right? The delta r is actually y final minus initial, right? When you say delta, is always final minus initial, right? Okay. So, let's say I thinking about, my bank account, right? So let's say initially I had $1,000. At the end of the month, I only have 300. The delta is 1,000 minus 300, right? Or otherwise, I spent $700, right? Okay. So in this aspect, right, we can define this thing called mgy, or mgh, sometimes you would see it as, right? Mass times the acceleration of gravity times h, right? We're just going to define that as potential energy, okay? Gravitational potential energy. I think usually it's a big G, right? mg times y, right? That's what we'll define it as, okay? Right? And that makes it pretty simple. Like, you just plug those in here, right? Instead of thinking about them as force times a distance, we're just thinking about them as a energy, right? Right? Okay. So, one more thing about energy before we move on to do the electric one, right? Up here in this diagram, right, with this y-axis here, right, I can make the y-axis 0 wherever I want, right? If I'm free to choose this y-axis, right, I can make y final equal to 0, right, and just shift this axis up a little bit, right? Or I can make y initial 0, right? And that changes actually the value of the potential energy we have, right? But it does not change the difference in energy. That's the important thing. It's actually the difference in energy that matters, okay? From the initial to the final, right? This change is actually the energy that's being converted basically from potential energy to, what do you guys think it is going to change into? Kinetic energy, because the object is now moving. Okay, great. Okay, so just be really careful about these zeros, because picking a good zero makes the problem much easier, much harder. Okay. All right. So now what we're going to do is going to go to the electric version of it. As opposed to an object falling in a gravitational field, we have some sort of positive charge being pushed in an electric field, right? Right? Whenever you have a charge in the electric field, there's going to be a force on it, right? The electric force, right, is just whatever that charge is times that electric field, right? This is what we learned from chapter 22 and 23. Okay, So what's going to happen is that if this electric field is set up between two parallel plates, where you have some positive plates here, some negative plates here, that's going to give you basically a constant electric field. Okay, it doesn't have to be constant, but just as this example, just like gravitation, right? We just wanted to start off with a example that is constant. Okay, gives you a constant electric field. That makes it nice because, right? The electric force is the electric field times the charge, right? And since we have a constant force, ds, I think that's the equation we started with. Since we have a constant force, we can bring this outside the integral and not have banging sound. Okay. You can bring this outside the integral, right? Therefore, it's the electric force integral of ds. That's basically the displacement of that object, right? So that's just Fe times. Actually, the book uses R instead, right? Let's just use R, the same as the book. Sorry about that. Okay. And since this is a dot product, it just gives you the cosine of the angle between them, right? Okay. Right, so the displacement is this way, the force is this way, so therefore the angle between them is actually 0. That gives you a factor of 1. In fact, we're just down here. Okay, so I'm just kind of replicating what's being done down here. Okay, so the electric force, right, is just the charge times the electric field. The displacement, instead of an x-axis or y-axis or z-axis, we're just going to pick an arbitrary axis called an s-axis, right? It's just a letter that's not one of those three, so it's not specific. Because you can, unlike gravity, right? Gravity always points down, right? Electric field, they can point whatever direction you want, right? So we're gonna make this abstract axis. So this, this S could be X, Y, Z, or combination of them, okay? So we're gonna have a initial position in the S axis, and then the particle is going to move from the initial position to the final position, and therefore delta R, right, is S final minus S initial. Okay, hopefully we're seeing the analogy here. Right now, if we just define this as the initial energy and this as the final energy, right, the change in electrical energy is actually negative of the amount of work that's been done by the electric field. Okay, you notice that there's a difference in the sign, right? You always, when you want delta, or you always want final minus initial, right? So this is actually backward. This equation is backward from this one. Okay, but what we can do is just define that as negative of the work, and therefore the electrical potential energy is some final energy, which is the charge times the electric field times the position of that particular particle, minus some initial version of it. What we can do is actually just call that U initial, right? Oops. I don't like the fact that they use O's and I's interchangeably, but that's okay. Okay. So that's the definition of electric potential energy. It's just the charge times the electric field times the position where they are, if we have a constant electric field. Okay, this is a big if. Okay. Okay. Remember, I was able to do this only because I was able to pull this electric force outside that integral, right? All right, so let's see what this looks like. Okay, once again, these energy diagrams. Okay. So this harkens back to our last semester, where we were just analyzing the energy of a system by plotting the potential energy as some blue line, right, on this blue line, okay? The total energy as some red line, I think it's like reddish, orangish, right, okay, right? And once again, the difference between the potential and the total is the kinetic energy, right? Because the energy always adds up to the total, right? And some part of it will be, right, E mechanical. You can even think of that as just kind of like E total. Okay, that's some potential energy plus some kinetic energy. We don't know what it is, but we know that they have to add up to the total. In the case where the energy of the system is conserved. Okay, if we start putting friction and all that stuff into play, then we're dealing with other stuff, right? Okay. Okay. Because it's kind of nice, right? So if I put a positive charge, let's say in the middle here, right? Thinking about like the gravitational version of this, right? Just the gravitational analogy. Where do you expect the little charge to move, left or right? If I put a little positive charge right here in this position, okay? This is where I put it, okay? S put. It's going to go left, right? Just imagine it rolling downhill, right? Because it's going to go from a place of high potential to a lower potential, okay? Right. So let's do an example so that we can actually see these with numbers, okay? So I used to work on this experiment called Lux, which creates an electric field, okay, by putting basically a bunch of positive charges up here and a bunch of negative charges down here, okay? Just like two parallel plates, okay? What happens is that when a particle from space comes in, what happens is that it'll strike the material inside here, which is actually a liquid xenon. I can even show you guys that if you guys are interested in my office, okay? What happens is that when the particle strikes the liquid xenon, some of the electrons gets free. So it's like you know, you take a little you take a baseball and you throw it, you know, at an object, and just kind of little pieces of the object just kind of flies out. Okay. These electrons initially are just kind of like, you know, scattering all around here. A bunch of electrons fly off. But since this is in an electric field, this electric field actually points which way, up or down? Down. It goes from positive to negative, right? That's a really bad color for that background. Let's not do that. Let's do green. Right? Right? And electrons go the opposite direction of the electric field, right? Because the charge is negative. So therefore, the electrons actually goes up to the top and it gets detected by some sensor, okay? What we want to do, oops, is to turn off the screen accidentally, is to figure out if the field between the anode and the cathode, okay, we don't have to worry about what those naming are, right? The positive plate and the negative plate is 1800 coulombs, so let's just start writing this down, right? Okay. The electric field strength, right, is actually in the negative j hat direction because it's downward, 1800 newtons per coulomb, okay? These plates are 50 centimeters apart, right? So let's just make that like the height of the detector, 0.50 meter, okay? If an electron begin halfway between the two plates, okay, meaning it actually started in the middle here, right? So that means delta y, right, is actually only 25 centimeters, right? Right. And it's asking you how fast will it be moving by the time it arrives at the anode, meaning it arrives at the positive plate. So this electron starts off halfway between the two plates and it's going to shoot up here, okay? So how do we calculate that? Okay. So the mass of electron is given up here. The charge of an electron is also given up here. So to solve this problem, we're going to use conservation of energy, right? So E mechanical, right, okay, is going to be potential energy plus some kinetic energy. We don't know what part is what yet, okay? But since we're dealing with an electron, we're not going to worry about the gravitational energy, right? Because electrons have such a small mass, it's not going to have a lot of gravitational energy. So the one we're going to worry about is electric potential energy, okay, which is actually, let's just write that down, right? The charge times the electric field, right, times, in this case, since we're moving in the y direction, we're going to have some y, right? Kinetic energy, as always, is 1/2 mv squared, right? You don't have to worry about which one is which. Okay. Okay. So what I'm going to do is I'm going to pick, let's do that in orange. I'm going to pick an x and y axis such that the electron started at y equal to 0. Okay. Why did I do that? We'll see. Okay. Right, you can pick a different starting. You can pick a different axis. You can start it down here, or you can start it on top. But I'm going to pick the middle one, and let's see how the math turns out. Okay, no matter which one you pick, it should come out. The answer should come out the same. But I'm going to pick this one because I think it's going to be the easiest. Okay, right. So what I'm going to do is I'm going to do conservation energy. The initial energy has to be the final energy, right? That's what it is. So the initial energy is the charge times the electric field times y initial, which is actually 0, right? Because it started off here, y initial, and then y final, right, is actually 0.25 meters up. Okay? Plus kinetic energy, since the electron kind of started off there, right? It didn't move yet. Right, the kinetic energy, so V is actually 0 there still. V initial go to 0, right? So therefore the kinetic energy is also 0. Okay, it seems like we're going to have a lot of zeros around. Okay. Okay, so electric field final, let's just keep chugging away at this, is the charge times E times Y final. Oops, that's the V. Y final. Okay. Plus 1/2 mv final square, right? I'm just putting F's on everything. Okay. So the left-hand side, right, is just 0. Okay. How is it possible that we're going to have some potential energy and some kinetic energy that's always going to, that's going to add up to 0? Is that possible? Right? Kinetic energy always has to be positive, right? Because it's this squared here, right? Can electric potential energy be negative? Sorry? Maybe? Well, let's see what happens. Okay? So we have 0 on the left-hand side. Q, right, is the charge of an electron, is negative 1.6 times 10 to the negative 19 coulomb. The electric field is 1800 newtons per coulomb. Y final is positive 2.25 meters. Right? Notice this negative sign, right, gives you a negative electric potential energy. Okay? And we still have 1/2 mv squared on the other side. Okay? So I'm going to plug in what the mass is. So if I solve this equation for V final, right, ooh, it's going to be 2 times 2 divided by the mass times 1.6 times 10 to the negative 19. The coulombs actually cancel out. 1800 and then 0.25 meters. Okay. Oops, and I didn't have the units for newtons here. Okay. All right, I'll put in the mass of an electron, which is 9.11 times 10 to the negative 31 kilograms. So everything is in SI units. Hopefully it'll work out. We'll see. I'll do a unit check after this anyway. Okay, 2 times 1.6 times 10 to the negative 19. Yeah, notice that, oops, I keep hitting this thing, right? The reason that instead of a negative, right, this is positive now because I moved everything to the left-hand side, right? And that's why the sign changed, okay? Just to make sure that's clear to everyone. Okay, times 0.25 divided by 9.1 to negative 31. All of that under a square root, okay? This number turned out to be basically 4.0 times 10 to the 7. The hope is that this is going to turn out to be meters per second, right? Let's double check that, okay? So inside here, right? The units inside is actually a Newton times a meter divided by kilogram, right? How is that the same thing as meters per second, right? Which of these is a base unit, which is a derived unit? Which one is a derived unit? Newtons, right? Newtons is a derived unit. 1 Newton, I'm going to write up here, right? It's a mass times the acceleration, right? So this should have kilogram. It's the same thing as kilograms meters per second square, right? So let's write that in. So kilogram meters per second square, and it's still multiplied by a meter divided by a kilogram, right? So the kilograms actually cancel out. So the units inside the square root is actually meters squared per second square, right? If you square root that whole thing, right, then it just knocks down the power of this, and you actually get meters per second as units. So hopefully that's a good check to make sure that you're not doing some, you didn't make a math mistake, right? Your units working out is a good way to check that you didn't make a algebra mistake, right? Okay. So this little electron is going to be flying at about 400 million meters per second by the time it hits the cathode, and which makes sense because electrons are such light, particles. It's going to be zipping around pretty fast. Okay. That's pretty normal for an electron. Any questions about this? Just applying what we did from last chapter to a slightly different potential energy, okay? Sorry, last semester. Okay? All right. Now, of point charges, we're going to move them around and see what happens, okay? So I'm going to set up an x and y axis here. Make the x-axis pretty long. We'll see why. Let's say I have a charge, right? And I'm going to be pretty smart and put the charge, right, at the origin. One charge. I'm going to call that Q1. Okay. So if I have another charge, right, that's very, very far away, right, I want to bring it over here some distance x from charge number 1. This is far away, okay? If I want to do that, okay, how much energy is that going to take, right? Because they're going to be repelling each other, right? It's like kind of like squishing two springs together. They're going to try to repel each other, right, if they're the same charge, right? Let's say both of these are positive, okay, for now. Okay. How much work do I have to do to push these charges in order for them to be so close to each other? Some distance x, which I wrote very badly. Okay. Okay. So this takes a little bit of calculus because, remember, the electric field from a point charge is not constant, right? It's 1 over 4 pi epsilon naught. The charge, and since this is the thing that's making the electric field, right, in every direction, right, we're concerned with the charge of charge number 1 divided by r squared in the r hat direction, right? If we're bringing this charge, I'm sorry I drew it up here actually. Keep changing the drawings on you guys, I'm sorry. Let's bring charge 2 from very, very far away, okay? If we're bringing charge 2 along the x direction, right, that electric field is going to be hitting that charge along the x direction also, right? So all of this, right, is going to be, right, along x. So let's just rewrite this as Q1. Instead of this distance r squared, which is the general distance, right, we're just traveling along x, so we just change that to x, and this is going to be in the I hat direction. Does that make sense? Where from just, setting my x-axis along the distance where they're going to, along the direction these charges are going to move, right? Instead of dealing with an arbitrary r, everything's just going to move in the x direction, okay? All right, so that's the electric field, right? The electric force, which is what we need in order to do our little integral, right, is charge times the electric field, right, from a point charge. Okay? Which Q should I be using, 1 or 2 in this case? 2, right? Because the electric field is acting on charge number 2 as it tries to get closer and closer, right? So the electric force is actually 1 over 4 pi epsilon naught Q1 times Q2 over x squared in the I hat direction, right? Now come the complicated part, where we're going to have to do an integral, because the amount of work it takes for us to bring that charge from far away to x equals to x, right, is some fancy integral of the force times did the book use S or R in first? Trying to be consistent. Yeah, they use R, so let's just use R. Okay, delta R, right? But since the electric force is only in the x direction, right, we're only concerned with the x direction, right? So let's plug this stuff in, this fancy integral, epsilon naught Q1, Q2, x direction, I hat, right? So I hat dot product it with, well, dr could be, you know, some d I hat, so sorry, some dx in the I hat direction, some dy in the j hat direction, some dz in the k hat direction, but this product, dot product, only picks out the parts that are parallel to each other, right? So these are actually going to dot product to 0, right? Does that make sense? Right? Because we're only picking, the force is only in x direction, so only this displacement we care about is actually the x direction. Right? So I dot I, since these are both unit vectors, they just dot into 1. Right? I hat dot I hat. Right? Both have, they're parallel to each other. Right? So it's 1 times cosine of 0. Right? Which is also 1. It's like 1 times 1 times 1. Okay? So hopefully that's clear. What I'm going to do is actually be a little smarter and bring all this constant out, right? So 1 over 4 pi epsilon naught is a constant. The charge is a constant, right? But as we move the object around, it's not going to change the charge, right? Q2. But this x down here is not a constant, right? It changes with x. So this is actually what we have. And then just this dx is left over here, right? So what's the integral of 1 over x squared? Anyone have that off the top of the head? That's differentiation, I think. Okay. So if differentiation, right, decreases the power, another way to write this actually, can I write it like this? Maybe the -2. Right? Differentiation decreases the power, integration increases the power, right? So this is actually going to be something x to the -1, right? But then you have to like bring down this 1 over that. Okay? Right? So it looks kind of complicated right now. Right? We're going to evaluate this from what? We started off at x equals to infinity, far away. Right? And we're going to bring it to x equals to x. Okay? Wait. Did I do that right? No. X equals to, yeah, we're starting at x equals, so this is a minus b, right? X equals to infinity to x equals to x. Right? Okay? So let's keep writing this. Right? So there's this stuff out front. That's a constant, which is nice, but it's just a lot of stuff to write down. Right? I'm going to rewrite this as -1 over x evaluated at x equals to infinity. What does that number turn out to be? 0, right? This goes to 0. We're going to minus -1 over x, right? Evaluated at x, right? These two signs actually cancel each other out. And therefore, right? The amount of work it takes for you to bring a charge from far, far away along the x-axis to x equals to x is 1 over 4 pi epsilon naught q1 over q2, right? And it's just 1 over x, okay? Okay. So that's if you brought it along the x-axis, okay? Right? If I brought it in some arbitrary direction, let's say in this direction, instead of the x-axis, it's just the r-axis, right? It's just the r direction, right? Because the electric field from a single charge is spherically symmetric, right? So in general, okay, right, this is actually the potential energy, okay? In general, the potential energy between two charges that you brought from far away towards each other, right, is this 1 over 4 pi epsilon naught thing. The two charges multiply together divided by r, okay? Be a little careful, right? Notice that this is r to the first power, right? The force is the one that's r squared, okay? Force is r squared. Potential energy is just r, okay? Okay. So the energy graph, when you bring these charges together, what happens is that there's a little problem here, right? If you can actually make r equal to 0, right, it actually has infinite energy, right? And the graph of this looks like this, where if you plot the potential energy between two charges as a function of r, as you decrease r to 0, it actually blows up to infinity. So it's actually not possible to put two of the same charges in the same spot. Okay? It'll take infinite amount of energy to do that. Okay? Okay. But what you can do is you take it from pretty far away, right? Let's say some r initial, and then you bring it in to some r final where the potential energy is increasing, right? But what happened is that you have some initial kinetic energy, so it's flying towards it, and then it slows down, slows down, slows down, until all of the kinetic energy gets converted into potential energy. Let's talk about what happens on the opposite case, where instead of the charges being the same sign, what if they're different signs, right? In this case, right, the electric potential energy, instead of being positive, is negative 1 over 4 pi epsilon naught q1, q2 with magnitudes, let's say, over r. Okay. Since this is a negative potential, it's actually unstable, meaning if you have a electron, who knows what the opposite charge version of an electron is? Anyone know what that name is? Positron, right? If an electron and a positrons are near each other, what will happen is that they'll get closer and closer together until they're both overlapping, and then basically a little tiny explosion occurs where all of their energy gets released as light, as photons. So this is why if you put matter and antimatter together, that's when things explode, if you ever had that problem. Okay. So what happened is that if you have the electrons, you have some positron here, you have some electrons, they're going to be attracted towards each other. Imagine this is like kind of like a hill, right? Where the electrons is just rolling down the hill faster and faster and faster until it basically gets to infinite energy, and then this little explosion happens when they're so close to each other that they're no longer separated. Okay. I think I'm going to end here and ask you guys to chat with me if you have any concern about the class. And then we'll do the multiple charges thing next time, okay? Let's see. We'll go here, stop recording.